Hey, what's up, Mr. Sutter here. Today we're going to be reviewing Newton's laws of motion and momentum. Let's get started. All right, so Newton's first law of motion says that an object at rest will remain at rest unless acted upon by an unbalanced force, and an object in motion continues in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This law is often called the law of inertia. Inertia is the tendency of an object to stay in motion. So on the bottom picture here, we have a sphere and it's rolling down the hill. Now, if there is no unbalanced force, the sphere will continue to roll on and on and on forever until an unbalanced force acts on it. That could be a person putting out their foot to stop the motion of the sphere, or it could be friction starting to slowly decrease the motion of the sphere until the sphere comes to a complete stop. So Newton's first law of motion is also the same reason why you should always wear your seatbelt. So in the first picture on the top, the car and the person are both moving at 60 miles an hour. In the second picture, the car crashes and slows down to 0 miles per hour. But now remember, that person that's inside was also moving at 60 miles an hour. So the car was moving at 60, but the person was also moving at 60. So even though the car stops, the person has inertia. Remember, an inertia says that an object in motion wants to stay in motion. So that person, their body wants to keep moving at 60 miles per hour. So because they don't have their seatbelt to stop them, the person ends up getting ejected from the car and then they get badly injured, which is always why it's super important to wear your seatbelt. All right, Newton's second law here. All right, so Newton's second law says that an acceleration is produced when a force acts on a mass. The greater the mass, the greater the amount of force that's needed to accelerate the object. Right, and we write that equation out as F is equal to m times a. Force is equal to mass, the mass of an object, times acceleration. So what does this mean? It means that heavier objects require more force to move the same distance as lighter objects. Let's take two examples here. So both of these objects have the same force being exerted on them. In the first example, we have a bullet here. It has a very small mass, and when it's acted upon by this force, it has a very large acceleration. However, when we apply that same force to a very large mass of the car here, the car has a very small acceleration because it has a much larger mass than the bullet. So the second law gives us an exact relationship between force, mass, and acceleration. It can be expressed as a mathematical equation. Again, F is equal to ma. Force is equal to mass times acceleration. So here's that equation again, where force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. Okay, let's look at an example of F equals ma. So Mike's car, which weighs 1,000 kilograms, is out of gas. Sucks for Mike. Mike is trying to push the car to a gas station, and he makes the car go 0.05 meters per second per second. Remember, meters per second is just another way to write meters per second squared. Right, so Mike's making this car go 0.05 meters per second squared. Using Newton's second law, you can compute how much force Mike is applying to the car. So we're going to use our formula. F is equal to ma. We substitute in here. So we're looking for force, we substitute in. So force is equal to 1,000 kilograms times 0.05 meters per second squared. 1,000 times 0.05. Our force is 50 newtons. Mike is pushing the car with a force of 50 newtons to the right. All right, now let's review mass versus weight. Now, in the beginning of the year, we also talked about mass versus weight, but it's a really tricky concept, and it's important to review it from time to time to make sure you remember the difference. All right, so mass is a measure of the inertia of an object. Mass is how much matter an object contains. However, weight is a measure of the force of gravity acting on an object. Let's say, for example, we have this astronaut here. So on Earth, the astronaut has a mass of 88 kilograms, and he has a weight of 863 newtons. However, on the moon or in space, the astronaut has a mass of 88 kilograms. The mass of the astronaut has not changed from Earth to space. No matter where the astronaut is, his mass is always going to be 88 kilograms. However, if you can see here, his weight changes. On Earth, the astronaut weighed 863 newtons, and in space, the astronaut weighs 141 newtons. Because the force of gravity is less in space than it is on Earth, the astronaut has a lower weight in space. So again, mass never changes. Mass is just the amount of matter that makes up an object, right? So your mass never changes. Weight changes because weight is a measure of the force of gravity acting on an object. All right, now let's look at Newton's third law of motion. All right, so Newton's third law of motion says that for every action, there is an equal and opposite reaction. So let's look at two examples here. So in this first one here, we have two boxers, and this one punches the other one in the chin. So the action is that the fist exerts a force on the jaw, but the reaction is that the jaw also exerts a force on the fist. And this is why boxers wear gloves, and it's usually why they tape up before they put their gloves on, because your knuckles are actually pretty fragile. So if you were to be in a boxing match and you were to not wear gloves, within the first round, after a few punches, your knuckles would probably break if you're a really heavy puncher, and depending on where you punch the other person. So wearing the gloves helps boxers to fight for longer because their hands don't hurt as much, right? Newton's cradle also is a good demonstration of Newton's third law of motion, and I'll show an example of that in a second. But down here is a good example of Newton's third law. So we have this man here. He pushes on the brick wall with a force of 100 newtons to the right, and the brick wall in response pushes back on him with a force of 100 newtons to the left. For every action, there is an equal and opposite reaction. So the man pushes on the wall, and the wall in return pushes back on him. Right, so Newton's third law also explains how the motion of rockets works. Right, so the rocket's action is to push down on the ground with the force of its powerful engines, and the reaction is that the ground pushes the rocket upwards with an equal force. So we have this rocket here, and it exerts some powerful exhaust to the left. Now, in response to that, the body of the rocket is going to move towards the right. So powerful exhaust comes out to the left, and the rocket moves towards the right. This is the same action that causes a balloon to fly away when you let the air out of it. The air is let out of the balloon on the left, and the reaction is that the balloon flies away to the right. All right, now we're going to talk about our last topic here. So this is momentum. Momentum is equal to the mass of an object times its velocity. And here's the equation. Momentum equals mass times velocity. So we have this baseball player here, and he's sliding into a base, and he has a momentum. He has a mass, and he has a velocity because he's moving in a certain direction. So when he stops running, he's stopping exerting a force. As soon as he is not running any longer, his velocity is going to start to decrease. But the reason he doesn't stop moving right away is because he has momentum. He has a mass and a velocity, so he's going to keep moving until his velocity slows down to zero when he safely reaches the base, right? So now that we know about momentum, we can talk about conserving momentum. Now, the law of conservation of momentum states that the total momentum in any interaction is not lost, it's only ever transferred. The exception is that if outside forces act on the object, the momentum can be lost. However, in a perfect world where there's no friction, there's no outside forces, momentum will never, ever be lost. So a good example of this is a Newton's cradle. So a Newton's cradle will transfer energy from one sphere through the other spheres to the sphere on the opposite side until enough energy is lost to friction that all motion stops. However, if there was no friction, the cradle would continue to move forever. Now, some of you may know I have one of these on my desk in school, and students have asked me, Mr. Sutta, if I pick up this sphere and I let it go, will it just move back and forth forever? And the answer in real life is no. Eventually, enough energy will be lost to friction that there will not be enough momentum in order to move the spheres any longer. However, if there was no friction, yes, indeed, the spheres would continue on to move back and forth forever. All right, that's going to wrap it up for our review of Newton's laws of motion and momentum. Thanks for watching. I hope you learned something, and I'll see you in the next video.